Welcome to the lecture on waves, beaches, and coast. I think it's entitled something slightly different in your textbook, but this is close enough. Um, Remember to start my timer. These can be only 15 minutes long. Just a reminder, bring your own water bottle, drink out of it. It's better than throwing away a lot of plastic. And it's also better than spelling things weird. Oh, man. Oops. There we go. Sorry about that. Um, Just some interesting stuff. Here is an earthquake in South Mexicali in 2008. Just wanted to show you, here are the fault lines, here where the earthquakes occur, and within a couple of weeks, here is an entire swarm of earthquakes that resulted from it. Kind of interesting. This is what the chapter is about. Moving property. Bummer. Let's look at waves first. What creates large ocean waves? Well, first, you have to have high speed of the wind, slow wind, no big waves, big wind, bigger waves. You want the wind to last a long time. If it's out there for just an hour and then goes away, let's say a whirlwind comes across the pond, you get waves, but not very big ones. If you get a hurricane that lasts for a few days, you'll get big waves. And then the last thing, fetch. Not like this. Fetch means the distance across which the wind blows. So imagine an ocean with a hurricane on it, 2,000 miles across, and let's see, the hurricane's out there for a couple of days blowing at 90 miles an hour. You're going to get big waves. On the other hand, if you have a pond, no matter what happens, you're not going to get big waves because there isn't a big fetch or distance. Some important concepts. The top of the wave is called the crest, the bottom is called the trough, and the difference between the crest and the trough in oceanography is called the wave height. In physics, it's half that distance. The distance between two crests or two troughs is called the wavelength. The wavelength is indicated by the Greek symbol lambda. A typical ocean wave is about 0.3 to 5 meters high. 5 meters is pretty high. Not unusual, you can get up to 15 meters, but the largest recorded, 34 meters, about 110 feet. I got a feeling the ones in that George Clooney fishing movie, Perfect Storm, probably made it look a little bit bigger than that, I'm not sure. Typical ocean wavelength is 40 to 400 meters, the distance between the crests or the troughs. And a typical open ocean wave speed, from 7 to 25 meters per second. For you guys in America, that's 15 to 55 miles per hour. Here is a crazy thing. Just got this out of Wired in January of 2012. There is a surfer trying to surf on what they believe is a 100-foot wave off the coast of Portugal. These huge waves are funneled because of an underwater canyon. This is just crazy. If you've ever seen the movie Gladiator, where Russell Crowe, Flavius Maximus or something like that, walks across the field of grain and swipes his hand across there, wave motion is kind of like that. In the movie, you see the wind moving the sheaves of grain or the stalks of grain. The weed itself doesn't really move. It stays attached to the ground. It's the same thing with water particles in a wave. The water particles circulate. This one bumps this one, which bumps this one, which bumps this one, which bumps this one. And the energy is transferred, but the water itself doesn't move. Sure, if you're on the boat, in a boat on the surface, you may get blown across, but the water itself isn't moving much. I know that's hard to believe. If you're ever scuba diving and snorkeling and there are big waves around, what do you do to get from being thrown around? Well, you just go further down. How far down do you need to go? Well, typically about half of the wavelength is the depth to which you need to go. Most of the wave motion is gone at that point. So again, the energy transfers, the water doesn't. This particle's high, this particle's low. That explains the wave motion. When a wave approaches a beach and the depth of the wave is about half of the wavelength, okay, half, that distance should be about half that, the wave will begin to have friction with the bottom. Now imagine you walking with your feet going more slowly than your head. That's what's going on with a wave here. The wave begins to slow down on the bottom, keeps the same speed at the top. That ends up forming breakers in the surf zone, which then hit the beach, and you have cool surfers on them, and those houses that you've seen before. Again, when the wave length, how do I put this? When the wave length is about, oh man, let's try this again. When the depth to the seafloor is about half the wavelength, then the breakers will start to form. That was hard. Those who are observant will notice something here. Look at the angle of the waves out here. Now look at the angle of the waves here. Something's going on. These angles are changing. They're becoming more perpendicular to the beach. This really does happen. Why? Well, imagine this is a line of trumpet players in a marching band. Trumpet player, trumpet player, trumpet player, trumpet player. You get the idea. And this trumpet player starts to slow down. The one out here keeps going at the normal speed. What will happen? The line will wrap around just like you do in formations in marching band. This is called wave refraction. Here's how it happens. The first part of the wave to hit slows down first. The rest of the wave keeps going faster, or its normal speed. Now this ends up creating what's called a longshore current. The waves are hitting at an angle, so let's say a little piece of styrofoam that you drop out here gets washed up, then back, then up, then back, then up, then back. Over a period of hours, that piece of styrofoam will get drifted down here. And then we will pick it up and put it where it needs to be. Also, you may have noticed this if you're out swimming and your parents are up here. You're out having a good time, and without noticing it, you're doing this. You look up, and even though you're in the same water you were in before, your family has moved, quote, quote, downstream. It wasn't the family that moved. It was you due to the longshore current. This is just kind of a cool little thing that shows a shallow thing underwater and then waves slowing down when they hit it. I'll have to repeat this a few times, but you get the idea. What is this thing? It's a very small example of a rip current. Here's a rip current. Notice the breakers out here. The wave bottom is hitting the sand underneath when it is about half of a wavelength, and they're starting to break. However, the water that comes up on the beach is heading back out to sea there. Don't get caught in these. They're hard. If you do get caught, don't fight against the current. Simply swim to the side and it becomes very easy to come back in. I know because I lived in a little island in the South Pacific. I'll show you in a while. And I got carried out. Me and two of my friends. They were married. They got yelled at. I was single. I didn't. I could make another comment, but I'm smart enough to stop there. Here are rip currents in Chile, which is spelled wrong. Take a look right here. Waters are coming up, but the rip current is right there. Now, don't think that the rip current blows you or tows you down. It's not an undertow. It doesn't grab you and pull you down where the big lobsters are and they're going to pinch your legs off. It's really on the surface, and it is underneath, but it's not going to pull you down. It just pulls you out. Again, if you get caught, swim to the side and then back in. Here's the water coming into the beach when waves are parallel to the beach. You'll notice that the waves are breaking out further. If water waves are not perpendicular to the beach, this is what you get, this kind of thing. Here's a little place in Tahiti. I stayed up this little road here once when I was living in Pongo Pongo. Wanted to come to a different island where they spoke French, so I came here, stayed with the family, harvested pineapples up below the mountain up this way, and then killed a pig for mon ami and sold it to Sonny's Magazine down here. At any rate, this is the reef around the island. This is just underneath the water right here. Here's a very safe area to swim back here. However, these areas right here, this is where the water goes back out to the ocean. This in Polynesian is known as the ava. Don't get caught in the ava. Again, if you do, swim to the side, come back over the reef. Be careful because you get scraped up there, but it's better than ending up way out here. Again, when waves come in at an angle, you're going to see this kind of up and back motion. It's a longshore current. Let's identify some parts. Here's the beach face, the berm, and the cliff. In a real beach, here's the beach face, the berm, and the cliff. Now, when are beaches bigger? Here you go. In winter, the big waves tend to eat away at the berm and the face. In the summer, Both tend to be a little bit bigger. Now, we were talking just a while ago about longshore currents. Let's say there's a dam up here, and it is blocking sediments from a river. The river used to bring sand down here, and the longshore current would bring the sand this way and block up this bay. Once we put the dam there, it blocks those sands, and these beaches begin to erode. Is it really happening? Yeah, even 70% of Hawaii's beaches are in retreat. There are dams there are buildings there that are blocking the sediments. Waikiki used to go way out here, the beach. Now it's this little narrow thing. Here is a baymouth bar. What am I talking about? When a longshore current creates sand across a bay, we get a baymouth bar. If it just sticks out there, it's called a spit. Here's a spit. Here's a baymouth bar. Here is a tombolo where this island is protecting the sand behind it. It's really kind of cool. Here is, I think, Point Reyes in California. This is the tombolo. Again, sand's being protected by the island. Folks, I made it in under 15 minutes. I'll see you in the next video.